President Kandel, President Hacker. It is a pleasure to be here. Dr. Baptiste and Dr. Zeisel, thank you very much for having me at Tamming. Jean-Paul, thank you very much to invite me to speak. It's of course a great honor to speak to this crowd. Ex-President Wittig, I'd like to recognize. He was the president of my university when I had a major active boost in or period of my career. So it's of course a great pleasure to have you all here and have this opportunity to speak to you all. I should also begin my talk by simply saying I'm not a roboticist by main training. In the time that I started my career, there was not much of robotics. We had trouble getting signals into computers via A to D converter, so having an A to D converter was the major hardware we had at the time. And so I devoted my career with other aspects of AI that I will speak about. The other thing I'd like to begin by saying is that much of my career and much of my research has been accompanied by a great friendship between Germany and France. We had wonderful research projects together. You see here just a small list of the various EU projects that we had, where we collaborated with a lot of the big name companies and research laboratories in France. STREPS integrated projects, large programs that the European Commission has funded, were always in great friendship between us in Germany and France. Personally, my family also has a lot of attachment to France because I grew up in Spain, so the country that I gotten to know the best was France by traveling through it all the time. And my parents always loved the time we spent in France. We also later participated in a major way in this initiative, Quero, which was a large national initiative that was initiated by Schröder and Merkel. And we were a proud participant in this together with the RWTH in Aachen. Again, major advances in our field have been achieved through this joint effort. We also set up a joint venture, IMI. It was a center set up between CNRS and KIT and RWTH, a joint venture of 3 organizations that once again was tremendously successful and a boost for all of the research that I will be presenting today. So let me talk a little bit about artificial intelligence. You hear, of course, a lot of it in the news. If you enter into your favorite search browser, the words AI is, you get the following answers. It's the new electricity, it is dangerous, it is the future, it is about creating a computer that can, it is bad, it is good, it's a new AI, and so forth. So what really is it? First of all, the good news, AI will add $15.7 trillion to the global economy by 2030. This is a study by PwC and predicts a major boost in profitability and revenue to companies around the world in this area of AI. AI will make life more convenient, it makes it more healthier, it's less tedious and repetitive, it removes boring chores. So many predictions will herald in a world close to a paradise of all these things that will be done by machines. And last not least, there are those amongst us who predict even religious overtones to all of this, where they say we can live forever by having an AI that will replace us or will live forward with us, with our spirit, and so on. I put a question mark behind it because I personally don't subscribe to this notion, but as I said, it's debated, of course, with great energy among philosophers and scientists. There are those of us who say AI is dangerous. It is seriously being predicted that it will kill 40% of present jobs, and this will, in fact, create a major challenge to policymakers and society moving forward. There is the worry about weaponization of AI. There is increased worry about whether we as humans will actually have a role when AI will take over many of our jobs. And the most sinister views, of course, is that humans will eventually only be batteries or attachments to the new generation or new evolution of humankind into machines. You see this all in the science fiction movies. You just have to go to cinemas. The most amusing and perhaps the most realistic one that I think is worrisome is this one here up here, which I think is already happening, is that we all kind of become fat, lazy, and entertained by machines and don't really have a purpose anymore. So this is a worry we need to work against. Whatever your belief in AI of the future, AI will be $1 trillion shift in wealth, and this is already happening. If you look at the size of the companies in 2006 and 2016, you see that almost all the major companies of 2006 were replaced by AI companies today. You see that Apple, Alphabet, Microsoft, Amazon, Facebook are now dominating and larger than what used to be Exxon, GE, Total, and Citibank. So these companies indeed are shrinking, are moving in the background, while AI companies move into the foreground. And it's happening at an unprecedented pace, very quickly. We see that this is turning things around in a very massive and a very aggressive way. You see the quotations, I will not read them all. The CEOs of all these companies essentially wrap the identity of their companies around AI. And in May, I was in China giving a keynote. It is well known that the president of the entire country of China views AI as one of their primary direction into the future. Now, who is to benefit? I just took a couple of companies and looked at their stock market value, and you see here some amazing curves. And please note that the lowest blue line down here, very down, is the Dow Jones average, which has had an enormous boost lately, but it is the minor one, and is essentially being pulled up by all these other companies that, in fact, adding this amazing wealth. To just not stretch your patience, the big one here is NVIDIA, and it's the company that makes the hardware on which all the machine learning algorithms today run. The others are Amazon, Google, Facebook, Microsoft, once again, all AI companies that are adding to their wealth. Now, what is AI and how did it come about? AI is a progression, is not new, really. It started in the 50s. The last of these founding fathers, Mr. Simon, Herb Simon, was among my doctoral committee. So I had the privilege of learning from the best and in fact, learning about their vision. But the field was a boom and bust. It was always promised to give us paradise on earth, and then it disappeared and people were disappointed. Technically, there was a progression from logic, rules, search algorithms, and finally machine learning to make learnable programs so that programs wouldn't have to be programmed all the time. Within this entire progression, my own personal dream was always to build a language interpretation machine. Having grown up in Spain, traveled through France, having German parents, studying in the United States and a Japanese wife, language always stared into my face as a communication barrier that needs to be overcome. Can we build this? In 1977, I proposed it to my advisor at MIT, said, I want to build an interpretation machine, and at the time we were barely beginning with speech synthesis. So luckily he was polite enough to send me back and to continue on my research, and said, that's a nice idea, Alex, go do your thing. Because I did not realize how hard the problem was and how much of fundamental AI problems it needed. Why? The world is ambiguous. There are lots of examples why we have trouble building machines that can really respond to common sense notions in the world. These are famous jokes, that range from the acoustic. If I say, give me a new display, give me a new display, it all is pronounced the same way. The semantics, the spirit is willing, but the flesh is weak, doesn't mean the vodka is good, but the meat is rotten. And if we say the baby does not like the milk, boil it, we don't mean the baby, but we mean the milk. And when you translate to another language, you need to understand those things in order to do this correctly. So in my career, it was always a search, building learnable machines that can generate abstractions, such that abstractions can be used in order to make a common sense understanding in the world. Now moving forward, today of course AI is largely identified with machine learning, and machine learning today is largely identified with neural networks and deep learning. So it's sort of a revolution, and everybody says deep learning is the big new thing. And the exciting part of this, of course, is that we can have now learning algorithms who we tell to do a particular task, and we never have to tell it what they have to do internally. The networks, through this algorithm backpropagation, really learn internal abstractions by themselves in order to perform their task. That, to me, was immediately attractive. During my PhD thesis, I tinkered with perceptrons, but they all had their limitations, and in came Jeff Hinton, one of the pioneers in this from San Diego. He was an assistant professor at Carnegie Mellon at the time, and he introduced me to this new algorithm backpropagation, which is what I was looking for all along. This is the algorithm that makes it possible to train large arrangements of networks such that the hidden representations can be inferred automatically. Now, backpropagation was invented in the 80s, so it's also not new. So the question, of course, arises, why now? Is this suddenly such a big discovery now after 20, 30 years at which we worked on this? For me, I began with speech recognition to apply it. Backpropagation on toy problems was fine and dandy, but we wanted to build systems that we can actually use in this vision of interpreting machines. We developed, Jeff Hinton, in discussion with Jeff Hinton, an idea that was called the time delay neural network, which created neural networks that are shift invariant, which means many pattern or AI problems are classification problems where we really don't know where the signal really is. You have to classify it, but you have to first find it in this input range. And I said this to Jeff and said, we will never make progress unless we have flexible classifiers that can classify even though you don't know where in the input range it is. So we came up with this idea of a shift invariant learnable backpropagation system, which we call the time delay neural network, which is shown here in 1987, and we applied it to speech with great success. It did what it was supposed to do, and it achieved really good results. We could show that the hidden representations can be taken out and transferred to new tasks so that we can again use what the network learns inside in new tasks and new problems. It can be combined and can be used. We built systems. We built systems that could spell, for example, directory assistance tasks. We can do handwriting recognition by creating, and this is all 1993, where even touch displays were difficult to find, and we had to build our own, etc., to do handwriting recognition and spelling recognition. Now, this didn't go unnoticed. This shift invariance is, of course, important in many other tasks. So it was recognized as an important element also for handwriting recognition. And so in offline handwriting recognition, so our friends, once again in France, adopted this notion and called it convolutional neural networks. These are networks that, once again, shift invariant, like our TDNNs, could now in the spatial domain recognize then images where, once again, you don't know where the signal is. Now, all this was great, and we had great fun in the 80s and 90s, but did it affect the world? Well, we had limited data. We had all these tricks to improve the models. They worked better than the other competing models, but we had great difficulty training them. I always had to take the Shinkansen to Tokyo and work this on the largest supercomputer that they had at the time to build these tiny nets that you could now compute on your watch or on your iPhone. And so the networks generated only modest advantage over standard techniques, and the standard techniques did fine in comparison. Performance was just only a little bit better, and they trained much faster. So the community largely ignored neural networks, and it essentially disappeared for 10, 20 years. Now time moved on, and this amazing Moore's law made sure that continuing improvements in computing happened. So in my career, there's a billion-fold increase in computing, 1 trillion in my lifetime. Storage has, of course, increased tremendously, again, through several orders of magnitude. And data, we're now building all of these systems in speech and language on more data than a human being speaks in their lifetime. So the amount of data is now exploding and is of course much larger than what human beings can actually ever use in their, or generate in their lifetime. So that made a big difference. Somebody, in fact Jeff Hinton, during a sabbatical at Microsoft, took those old networks and tried them again. And wow, lo and behold, what happened was, while the other methods kind of plateaued in the 90s and 2000, neural networks kept on going. By adding more layers to these networks, we would actually improve results and generate an improvement of 30% of relative error reduction. And again, keep in mind, speech recognition is an area where people kill over 0.5%. 30% is unheard of, is totally unreasonable, and was amazing. So it took the field by storm. Machine translation, financial engineering, all these other things followed. And of course, we added more layers. Nota bene, this was also interesting because at the time we were told that we should never add more than one hidden layer, because a neural network with one hidden layer can represent any nonlinear decision surface you can imagine. So if you went in the 80s or 90s to a conference and showed a network with 2 hidden layers, the mathematicians told you, no, 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 1 layer is enough. Why are you wasting resources? Well, it turns out now, every time you add a layer, things improve. And Microsoft and large companies are now in the order of hundreds of layers, building enormous networks, and things are still getting better. So don't trust the mathematicians. I'm kidding. Now our networks got larger. We now began to build large networks for speech recognition again, just like based on the same old models that we had below. Microsoft reported that they can now reach superhuman performance, or reach human performance in speech recognition, once again with TDNNs and convolutional neural networks. You see the team here. Our friends in Toronto applied this to major image recognition tasks and showed that, again, shift invariant neural networks now reach reach the best results in image processing, and you know the story about AlphaGo. For us, it meant automatic language interpretation. We built a system that from 1991 to 2009 that became a company that later got acquired by Facebook, so I spent some time there building this, and we're now developing large interpreting systems that we run at the university to interpret lectures for foreign students that come to University of Karlsruhe or Karlsruhe Institute of Technology. We're doing initial tests with the European Parliament to see if the Parliament can be supported by automatic technology with great interest. You see here the Secretary General of the Parliament who is supporting this a great deal. Now, where is AI today and where is it leading? Since I'm getting the evil eye of time here, let me accelerate all of this. Not all is well. So there's a lot still to be done. My favorite reason to ask you, why is not, if you can do Go, AlphaGo, isn't the problem of AI solved? Well, consider a plumber. A plumber makes $200,000 salary, and there is no hope in sight that you can replace a plumber by an AI system. And ask yourself the question, why is this the case? Well, first of all, it's an unpleasant job. Secondly, it's something that requires a great deal of creativity, if you think about it, because every house is different, every pipe is different, every constraint is different, and it is a social skill as well. So all of these things come together into something that we simply can't do by machine. Robots, this is a project that Tamim Asfour is leading, and we're collaborating on this. We're doing the interface with it. It's a great opportunity to begin looking at robots that interact with humans, doing collaborative work between humans and machines, which I think is a way for the future to do it in this way. So this gets us to a whole bunch of things that are still not solved. Humans learn very differently. They can do the physical and the mental and the multimodal perception. We self-assess, we can explain ourselves, we can learn from feedback and errors individually. We learn incrementally and continuously. We learn with little or no data. We sleep over it sometimes. We literally learn on data we produce for ourselves at night without input. And we forgot the unimportant and we retain the important. Nothing of that can be done by AI today. We learn interactively and socially, and we love and we feel. Let me shift gear a little bit, since I'm already out of time, but I want to still get a very important message in. Politically, what does this all mean to Europe? As you all know, there is a rift with the US. Don't give up on the US. Again, part of my activities in the US, and I believe there's many friendly people who don't believe in this rift, but once again, I think there's a great collaboration to be had. Now, is Europe underinvested or ill-invested? If we look at the budgets, we see that Europe as a whole actually spends a healthy amount of money on research. But we see two interesting trends. One is that China is coming up with an incredible aggressive speed in terms of funding. And the US budgets, as we see in a moment here, are now flat. So much of the research budgets in the US now are coming increasingly from large corporations, not from the federal government anymore. Publications are increasingly decreasing by US scientists and increasing by Chinese scientists. So where does that leave us all, and where should we invest? So if the money is okay in Europe, are we perhaps ill-invested? My feeling is that one of the things that Europe is doing really well is the basic science and also the manufacturing at great scale. Where we're lacking is the transition, where things are being transitioned from initial crazy ideas to transfer into major businesses. Now, if you look at the US budget and see where it comes from, most of it, or half of it, comes from DoD. And so that's why I want to spend a little time on DARPA, because we hear a lot about a European DARPA, because it is one such mechanism for mission-oriented research transfer. Is the D important? Do we have to have defense-related research? And I think it's important politically to understand that D is used as a strategy in America in order to create mission-oriented research, not necessarily that it's all for military purposes, but because it gives you the opportunity to create focused research on large moonshot problems, to get something done. And that can then sell it politically at its sponsor, and then also the government can become the customer of such research, and we can do large things. Examples abound: the internet, stealth, the computers, self-driving cars, all are inventions by DARPA over time. And the key ingredient to it is speed. DARPA has an amazing ability to have flexibility in spending, rapid redirections, budgets for new ideas, seedlings and discretionary, and the projects are defined and initiated. A key element to it is the program manager, and I'd like to emphasize this because I think this is an important element for Europe that Europe does not have right now. The political mechanisms for doing large research projects are also consensus-driven. They are large committee-based things, and they lack the speed to do moonshot projects effectively. DARPA has that ability of creating a large vision and then appointing a program manager who for 4 years has total dictatorial control over the budgets. They can spend it as they please, but after 4 years they get kicked out. And that's a good mechanism because it allows for a scientist who is on loan to DARPA to really create an initiative that is dictated by scientific discoveries. And so this freedom generates speed, and the speed generates then breakthrough results that are important. The other element, of course, again, of speed is American companies, where venture capital and ventures is a key element. And here my wish is to create better mergers and acquisitions mechanisms, because as one of my friends from Switzerland said, the greatest ambition and the greatest hope for a European entrepreneur is to be bought by an American company. That should not be the case. We have to create better mechanisms for mergers and acquisitions in Europe. So with this, I conclude. Yes, there is a rift, but don't give up on the US. China has dramatic growth. We need to respond. The R&D needs to continue to be funded and supported well. in Europe we need a DARPA, we need a mission-oriented research organization, we need better mergers and acquisitions for faster transfer of productive ideas. And in the last not least, the good news is the creative artistic talents of Europeans will ultimately also provide an amazing advantage in terms of actually bringing a collaborative notion into AI where humans cooperate with machines in a positive coexistence. Thank you.